Engineering from the group of Dr. Chuang will present photocatalytic reaction pathways for organics on TiO2, and our presenter will be Felipe Guzman.
Thank you very much. We'll try to make this brief so everybody can have lunch. And I'm very happy to be here and excited to show you the fascinating results that we have been obtaining on the photocatalytic reaction pathways of organics on titanium dioxide. Let me begin by giving a brief introduction in photocatalysis, and I hope this complements what it has been said before in the previous presentation. The objective of the photocatalysis is to generate chemical reactions by introducing a substance that absorbs light and is involved in the subsequent chemical transformations. Now, within the heterogeneous photocatalytic processes, there are two, you can classify them as two major kind of processes. The first one is the catalyzed photoreactions, and the second is sensitized photoreactions. In catalyzed photoreactions, the absorption of light occurs on a molecule that is absorbed on the surface of the catalyst, and the initial excitation proceeds later on, and the reaction continues starting from that photoexcitation. In the sensitized case, is the substrate who is first absorbing the light and being activated, and it transfers electron or energy to absorb species, and that's how the reaction is started. We are particularly interested in this type of reactions, and more specifically, we wanted to study semiconductor catalysts such as titanium dioxide. I also would like to make a few comments on the semiconductor electronic excitation process. Now, this sketch that I put here shows how after light absorption, the electron and hole pairs are created, and these electron and hole can undergo different paths. And depending on those paths, the quantum yield, which is referred to as the number of events that occur per photon absorbed, will change. The quantum efficiency will change. Now, the hole and electron can migrate to the surface and undergo recombination. They can also recombinate in the bulk, as I'm showing pathway 2. And in pathway 3 and 4, the electron can go migrate to the surface and transfer electron to an acceptor molecule, and the hole to a donor molecule, and create ions that will continue the reaction. I also would like to make a few comments on the reaction steps in photocatalysis. Now, the first step that I already talked about is the absorption of light, creating electron and hole pairs. Now, water in the surface of the catalyst can also react with hole and produce hydroxyl radicals. And the oxygen can also react with electrons, producing oxygen ion. Oxygen ions, in turn, can further react with water and produce more hydroxyl radicals. And I would like to stress that these species, the holes and the hydroxyl radicals, are species that are active and promote the oxidation reactions. Now, this sketch shows that. Now, in this slide, I wanted to point out another research finding that we found very useful in our research, and is that under certain circumstances, IR can be used to detect the photogenerated electrons on the surface of the catalyst. Now, these special circumstances in which that you can see the IR absorbance of electrons requires the oxygen to be absent, because oxygen can react with electrons producing the oxygen ion, and if this happens, then the electron will be depleted. So if you can produce a medium where there is not much oxygen, that is achieved mainly in vacuum, and you remove the water from the surface, you might be able to see an absorption due to the electrons And this creates a background shift in this example that we saw in our lab. You can see how at 0 minutes, this is the background, the IR spectra, and after 30 minutes of irradiation, the whole background shifts up because of this absorbance of IR by the electrons. Now, the objective of the work that I'm showing here was to determine the reaction pathways during the photocatalytic oxidation of organic molecules using ethanol as a model compound. And we also wanted to use IR as a tool that can allow us to probe the relation between photo-generated electrons and absorbed species in the ethanol photo-oxidation. Let me talk about the experimental apparatus that we use. This experimental apparatus is very simple and is composed of 3 main parts. The first part is a drift reactor that resides inside a FTIR bench. And it has, it's enclosed by a dome that contains 3 windows. 2 of these windows are IR transparent, and the third window here allows the UV irradiation. Now the second part of the equipment is a UV lamp, and we also have a manifold to allow the introduction of oxygen and ethanol into the reactor. Now let me show you the results that we obtained during this photocatalytic oxidation study. Initially, I'm going to discuss the absorption of ethanol on the titanium surface. We tried 2 different cases, one that we call the low coverage ethanol and one that we call high coverage ethanol. In the case of low coverage ethanol, we flow oxygen and ethanol for 2 seconds, and after that, we flow oxygen for 20 minutes to remove all the vapor phase ethanol remaining inside the reactor. And as you can see, I want to point out that this IR spectra allows us to see that ethanol absorbed in 2 main modes, as molecularly absorbed ethanol and as dissociatively absorbed ethanol. And we can see here the bands, characteristics of this. And I also wanted to point out that water has been displaced from the surface. And it creates also a negative band in the hydroxyl band at 3690 wave number. Now we did similar procedure in the high coverage ethanol. We flow for 10 minutes oxygen ethanol, and then we purge with oxygen for 20 minutes to remove all gas phase ethanol. And again, we see the displacement of water marked by this band. And we also see the absorption of ethanol molecularly and dissociatively absorbed. Now let me show you the results of oxidation in intermediate. Since the bands, most of the bands of the intermediate species that will appear during the oxidation will overlap with those of the reactants, we took the spectra and subtracted the initial time when the reaction starts. So that's why the first spectra that I'm showing is a flat line, which is 0 minutes subtracting 0 minutes. And as reaction goes by, you can see how these positive bands indicate products being formed, and these negative bands indicate the reactants being consumed. Now here we can see the characteristic bands of the ethanol being consumed, the asymmetric vibration of CH3 at 2971 wave number, the asymmetric vibrational frequency of CH2 at 2931, and the symmetric vibration of CH3. Similarly, we see during the photocatalytic oxidation, water is being developed, as it showed in this band at 3550. And the hydroxyl group is also creating a positive band at 3692. Now, and of course CO2 is being produced as a main product, one of the main products of the reaction. Now, I would like to show the detail of the first 2 minutes of photocatalytic oxidation in low coverage case. In this case, we can see that CO2s are producing since the beginning, and we see three major species, which are the formic acid, the formaldehyde, and the formate, They are characterized by these bands that I'm showing here, 1691, 1619, and the formate bands, as I'm showing. Now, to confirm that the band assignment was carefully done and it was correct, we run the formic acid oxidation. And in this case, we repeat similar procedure as I explained before, and oxidize the formic acid, and we can see how the formic acid creates a negative band that indicates its consumption at that very same wave number. So we confirm the assignment of formic acid and also the formate. Now, this formic acid reaction occurs by a oxidation reaction pathway in which formate is formed, and after formate is formed, water and CO2 is further produced. Now let's come back to the 120 minutes of photocatalytic oxidation in the low coverage case. We can see here that as the reaction continues to proceed, more formate is being observed, and a prominent band of acetaldehyde appears, as well as an increase, significant increase, in the bands corresponding to acetate. I am not showing them here because it would be very crowded, but their locations are at 1450 and 1550 wave numbers. Now, this figure that I'm showing here, we wanted to make sure that the assignment of the acetaldehyde was correct, and we run a similar experiment in which we absorb acetaldehyde on the titanium surface, and we confirm that the band assignment has been correct. Now, with this information and our further analysis, like I'm showing here in this figure, the IR normalized intensity change during the photocatalytic oxidation, the first intensity rises on the formate until reaching a maximum, and then it starts decaying. And the formic acid formation led the formation of formate, and in turn, formate led the formation of acetate and acetaldehyde. Now, with these results, we wanted to propose a low coverage mechanism for the photocatalytic oxidation. As I mentioned before, the ethanol can absorb as molecularly absorbed ethanol and dissociatively absorbed ethanol. And we propose a pathway A in which the surface that contains a lot of water can undergo oxidation by hydroxyl radical, producing directly formic acid and formate by attacking beta carbon. And this has been documented in previous research studies. Now, as the reaction proceeds, we start seeing the development of the acetaldehyde, acetic acid, and acetate as the reaction continues in a different, following this pathway. Now, in the case of high coverage photocatalytic oxidation, again, we see the production of water, the consumption of ethanol, and of course the production of CO2. And in this case, after the 120 minutes of reaction, acetaldehyde becomes one of the prominent bands, and acetate is constantly being produced since the beginning of reaction. To make sure that we had correct band assignment, we run the acetate oxidation, and we confirm that, as you can see in these bands, 1542 and 1446 correspond to the acetate in the acetate oxidation consumption, and in our case here it's being produced as intermediate species. And we propose a high coverage oxidation mechanism in which, in this case, the surface of our catalyst, since it's a high coverage, has less water available, and the reaction is likely to occur via a Hall-initiated pathway in which holes promote the formation of acetaldehyde, acetic acid, and as the reaction proceeds, more water is available in the surface. More water is available in the surface, and that can produce activate the pathway A and produce formic acid in the formate. I am showing here one of the interesting results that we found, and is that during the high coverage case, since ethanol is displacing a lot of water in the surface of the catalyst, we can actually see the IR absorption of electrons trapped on the surface. As you can see here, how the background shift changes. And as the reaction proceeds, more water is available, and this background shift shifts down again. As I'm showing here on the normalized intensity, the water is being produced, and as the water reaches a certain limit, the background shifts back again. Again, we want to summarize the reaction pathways that we found or that we proposed. In the case of low coverage, the surface contains ethanol absorbed as dissociatively absorbed or molecularly absorbed ethanol, and the reaction can proceed very fast, producing CO2 water without electron trapping and producing forming major intermediate species. And in the high coverage case, it can produce CO2 and water more slowly, and there is an electron trapping and production of acetate, and it's whole initiated. And, we also conclude that the turnover frequency of the CO2 formation were found to be significantly lower than those for the CH breaking, indicating that the conversion of intermediate species is a rate limiting step in this oxidation process. Thank you.
Floor is open for questions for Philippe. They're all hungry, I think. Well, Rajesh.
You absorb the ethanol first, I guess, and then you dissolved it, whatever was free ethanol from there. So, and then you pass oxygen after that.
We absorb we flow the ethanol and oxygen. It absorbs on the surface for a certain amount of time, and then we step switch to oxygen to purge all the gas phase species.
Okay. And then oxygen is continuously purging after that.
No, the reactor is switched to batch mode.
Okay.
And then the light is being.
So then I see that after 120 minutes you still have CO2 producing. So this is, I guess, a very slow reaction.
It is very fast at the beginning, but the formation of intermediates is the rate limiting step. That's
Are there any other questions? Do you see actual differences when you use rutile or anodized?
Or in all this research, we have done only one type of titanium we haven't tried.
Well, please help me thank Philippe one more time.